And most of us, we go about our daily lives not thinking about it so much because it is so predictable. And we think we know the sun. But do we really? Well, when we can see the sun in all its glory, we will learn much more about ourselves and our place in the universe. But let's just start with the basics. There are certain times when we're lucky enough that we see an astronomical miracle. That is a total solar eclipse. May I ask you, how many of you managed to get a glimpse of the total solar eclipse in 2017? Wow, that's at least half of you here. How many of you think that it was worth the 5-hour drive, the 10-hour drive? Basically, almost the same set of hands. And I would agree. This is what I tell people. An annular eclipse is beautiful. You see a ring. A partial eclipse is not bad. You get to see the moon in front of the sun. But a total eclipse is a completely different thing. It's a life-changing experience. The reason it is so different is that the light from the disk of the sun is about 1 million times brighter than the light we see from the solar corona that we can see when the moon completely obscures the solar disk. And it is, at least on Earth, unless if you have a special telescope, only during these times that you can see how structured, how wonderful it is with all these striations, that is the solar corona. We find that this is not a boring, spherically symmetric structure at all, but it is different from eclipse to eclipse. And beyond that, the experience one gets from anticipating the totality, from seeing the surroundings change from the normal green, the normal colors in the field, to some metallic indigo. That is unforgettable. So when you get another chance in a few years, when we have another total solar eclipse crossing the US, I urge you, don't be like some of the citizens of Portland who said, oh, the eclipse is coming to us, so why drive that's 20 miles south to see totality? I urge you to make that extra effort and experience it for yourself. So this is usually what we see, but we're advised not to look at the sun directly. But suppose you have the right filters, then this is the solar disk. Sometimes there are blemishes, dark spots, very faint dark spots that you can see here. And if we stare at it for a day or so, we realize that the sun is rotating, the spots are moving. But still, it doesn't look that spectacular. But if we can get out of the Earth's atmosphere, get above, and image the sun in other light, then we see that during the exact same time period, something extraordinary is happening. The solar corona here is pinching off to create a coronal mass ejection and a solar flare. And we would like to know what these are. But in order to do so, let's have a basic introduction to the electromagnetic spectrum. Until a few years ago, most of what we learn about the universe is from measuring electromagnetic waves arriving at the Earth, or from energetic particles that are hurtling through space and near the speed of light. But now we have also gravitational waves from LIGO, and that's opened an entire new window. But still, most of what we know is from the electromagnetic spectrum. And these are wiggles of the electric field and magnetic field in space. And these waves can have different wavelengths. You can have radio waves that are very long wavelength, maybe the size of buildings. You can have all the way to gamma rays, which are even smaller or comparable to the size of atomic nuclei. And then there's everything in between. And then there's the visible spectrum that we see. And actually, the sun emits in all these wavelengths. And observations of the sun in all these wavelengths, different wavelengths, tell us something a little different. And so, when we see the sun in the different wavelengths, in the different new lights, we learn so much more. This is back to a visible image of the sun, now near solar maximum, so that there are more sunspots and bigger sunspots. And people have been drawing sunspots for a long time and continue to do so, even though we can capture regularly photographs of sunspots. And this is a beautiful sunspot drawing from Mount Wilson Observatory near Los Angeles. Bless them for doing this work every day. It's so pretty. This is one of the largest sunspots. This was the largest sunspot in the last 30 years. Well, how large? It's this large. So, sunspots are planet-sized objects, holes that seem to be punched into the surface of the sun. And it used to be that some scientists considered that these were openings into the sun, and you can peek and see living beings underneath. But that is not the case. And people have been drawing sunspots and counting sunspots for hundreds of years. For example, Galileo reported that the sunspots were traversing the surface of the sun. And other natural philosophers, they counted sunspots and they found that there is an approximate 11-year cycle. That's the number of sunspots on the sun on any given day waxes and wanes with an 11-year period. And in the modern space age, when we can measure the emission from the sun's corona, which is plasma at millions of Kelvin, we see also that the brightness there varies with the same periodicity. But what are these sunspots? And do they affect us? So it was in 1859 when Richard Carrington and Richard Hodgson in England, they had their telescopes on one of these sunspots, and what Richard Carrington saw was a flare. He saw these bright ribbons light up on the surface of the sun in between spots, and he was very excited. He didn't know what it was, but he reported it. And then, at around the same time, actually, even before, a few days before his observations and after, people were reporting aurora. And not just the aurora in the northern or southern regions. People reported auroral sightings in large swaths of the globe, in places at low latitudes that you would not typically see aurora. So this is a graph, a plot from a recent paper where they went through more historical records, and in the red dots are the they added these auroral sightings to what people knew were places where people reported aurora pretty soon after Carrington's solar flare. And in addition to seeing these aurora where you usually wouldn't see them, people were also measuring magnetic fields on Earth. At the time, they had magnetometers, a legacy of Alexander von Humboldt. They found huge disturbances, much more than typically you would get, at around the same time. And so it was very strange. And I think at that time, it would have been have frowned upon if someone told you that whatever happened on the sun would affect the magnetic fields on Earth, but that is common knowledge today. And the scientists who transformed our view of the sun is George Ellery Hale. 101 years ago, he used the newly discovered quantum mechanics, the so-called Saimin Effect, which says that some energy levels in atoms split when the atom is in a magnetic field, in a strong magnetic field. So usually with these energy transitions, you might have some absorption lines in the solar spectrum, but then these absorption lines, each one absorption line will suddenly split in the presence of a magnetic field. And from the distance in the splitting, he inferred that there were very, very strong magnetic fields in sunspots. And that suddenly gave us a hint that there might be an agent for how the sun might be able to disturb its surroundings, including on Earth. So how does one actually do this? So imagine you're at a movie theater watching some 3D movie, and they give you these glasses. And so the ones where the image doesn't split when you tilt your head, what it does is that one lens would let light that is spinning clockwise through to your eyes, and the other lens would let light spinning counterclockwise through your eyes, and then your brain would, your visual cortex system would add the images together, and because of parallax, you get that 3D image. Okay, so now imagine, this is what I mean. So imagine you did that. You measured the left spinning light from the sun. You measure the right spinning light from the sun. Instead of adding, you subtract. So these almost look like identical images. But if you did it at certain specific wavelengths, using the properties of atoms, what you find is that when you subtract these two images together, it looks like this. This is a magnetic map of the surface of the sun. So by using these techniques, we can regularly observe magnetic fields on the sun, and what we find is that the magnetic fields are not just concentrated in sunspots, but also in the peripheries of sunspots, and even in the quiet regions away from the sunspots. The magnetic field is everywhere. But the thing about magnetic field is that magnetic fields have no end. From your high school physics, the divergence of the magnetic field is zero, it's solenoidal. It has no end, so what comes up must eventually go down. So you have magnetic fields that are coming out of the sun and into the sun, and this is denoted by the white and black polarities here. So that's interesting. The sunspot groups are big magnetic loops. And when you observe a movie of these magnetic maps, you see, first of all, that the sun is rotating. It rotates about once a month, depends on where you're tracking. But you also see that there are flows streaming out of sunspots with carrying the magnetic field. There is a network pattern that is called the supergranulation that is dispersing the magnetic field from the sunspot regions. And eventually, some of this magnetic flux cancel with each other. Others get affected to the polar regions of the sun. And then people have theories about how the sun reverses its polarity every 11 years, so that the magnetic cycle is not 11 years, but it takes 2 sunspot cycles for the magnetic field to reverse every 22 years. This is the secret life of the magnetic sun. And this is the reason why the sun is so interesting and so dynamic. When we look at one of the sunspots this is a ground-based telescope, in high resolution, you see what is the umbra, which is the darkest part, and then you have the penumbra. And by the way, around the sunspots, these blobby structures are called granules. They are indicative of convection, and each one is about the size of, let's say, California or Texas or Germany, huge things, but they only last 10 or 20 minutes. That's how dynamic the sun is. And because we can measure the magnetic fields with the technique I just mentioned, we find that in the penumbra, the magnetic field is about 0.1 to 0.2 Tesla. And in the umbra, it's about 0.3, maybe 0.4 or 5 Tesla. And by Tesla, I don't mean that you can have 3 umbra to buy a Model X. That's not what I mean at all, even though it's all attractive. It's a unit of the strength of the magnetic field. And to give you an idea of how strong these fields are, these are the field strengths that you would typically have in a magnetic resonance imaging machine. And you're not supposed to have metallic materials on your body when you go to one of these MRI scans, because the magnetic field is so strong that it will rip things out. So sunspots are like planet-sized MRI machines. Think of it that way. Extremely strong magnetic fields. And if you have the chance to see the Skylab out in the Space Hall, I encourage you to do so, because other than a lot of experiments and giving a lot of astronauts experience with living in space, Skylab was special for solar physicists because of the Apollo telescope mounts. The Apollo telescope mounts had, I think, maybe 7 or 8 solar telescopes that were pointing at the sun, free from the absorption in the Earth's atmosphere, free from seeing. And at that time, it was one of the golden ages of solar physics. You had literally astronauts doing spacewalks to change the film. They were having telecons with the scientists on the ground, deciding which part of the sun to measure.